Welcome back to AI 101. I am Maya, and today we are tackling a counterintuitive puzzle. Imagine you switch your coding agent to a model that is technically faster and cheaper per token, but somehow your tasks take longer and cost more.
I am Theo. It sounds impossible, right? If the brain is processing words faster, the job should finish faster. But as of 2026, agent economics simply do not work that way.
The key is remembering everything we have discussed in the last two episodes. An agent is not just generating one long essay, it is running an iterative loop. It is taking laps.
And because it is taking laps, raw reading and writing speed is only half the picture. Today, we're going to look at the hidden multiplier that makes a highly capable model dramatically cheaper to use in practice than a so-called budget model. Quick, honest note before we dive in. This is an education series, not advice of any kind. We are just two curious people trying to make AI make sense.
And AI moves fast, so everything here is how things work as of 2026, and it will keep changing. Treat it as a map, not gospel. The real learning happens when you go and try it yourself. Let us introduce the master variable of agent performance, turn count, or as we called it earlier, laps. How many back and forth loops does it take to finish the job?
A strong, highly capable model plans ahead. It looks at an error, understands exactly which file contains the bug, and picks the right tool on the first try. It might solve your issue in 3 lean laps.
A weaker model, on the other hand, flails. It guesses incorrectly. It edits the wrong file, sees a new error, gets confused, rereads the entire directory, and tries again. It might take 18 laps to achieve the exact same result.
That difference in laps changes everything. You are paying for the execution time of 18 tool calls instead of 3. But more importantly, you're paying a massive hidden tax on the context window.
Let us talk about that hidden tax. The hidden multiplier in agent architectures is that the conversation transcript grows longer on every single lap.
Remember, the brain is stateless. On lap 1, it reads your prompt. On lap 2, it reads your prompt, its previous tool call, and the tool's result. On lap 18, it is reading a massive history of every single mistake it has made so far.
Every time you add a lap, you are resending that entire ballooning transcript. This means the cost is not linear. Cost in an agent loop trends toward quadratic growth. You are paying for the history over and over again.
So a cheaper model that needs many laps is rereading a massive history every time it wakes up. The cost of those extra laps quickly eclipses the savings of the cheaper per token price.
Now, we have to introduce a massive, important caveat here. If you are a developer, you might be shouting at your screen right now saying, "What about prompt caching?"
Yes, absolutely. In practice, all major harnesses use a technology called prompt caching. This allows the system to cache the stable, unchanging prefix of the conversation.
Because the beginning of the transcript does not change, it is just being appended to. The provider can cache that massive history. So resending it on lap 18 is significantly cheaper and faster than processing it from scratch.
Prompt caching softens the blow of that quadratic growth. It prevents the system from grinding to an absolute halt. But it does not erase the cost entirely. Resending and re-verifying a massive, flailing history is still much more expensive than just finishing the job in 3 laps.
Exactly. Caching softens the curve, but it does not repeal the laws of physics. More laps still equal geometrically more overhead.
Let us look at a toy example to illustrate this. These numbers are purely illustrative, but roughly speaking, imagine a highly capable model finishes a task in 6 lean laps.
Because it gets right to the point, the transcript stays short. Across those 6 laps, it might process roughly 50,000 tokens in total.
Now, take a weaker model. It flails and struggles, taking 18 laps. Because the transcript grows so much larger, across those 18 laps, it might process 350,000 tokens.
So it took 3 times as many laps, but processed 7 times as many tokens. Very roughly. That is 7 times the cost for 3 times the laps, even before factoring in caching discounts. This is why a model that is half the price per token can still cost you 3 times as much for the total task.
This brings us to an interesting insight about model behavior. Sometimes you will use a model that seems very terse. It does not explain its reasoning. It just outputs the tool call.
You might think, oh, it is writing less, so it must be cheaper. But less visible thinking is not less work. If that terse model makes poor decisions and needs more laps, it is far more expensive.
A model that writes a long, thoughtful paragraph before calling a tool might seem like it is wasting tokens. But if that thinking out loud helps it pick the correct tool on the first try, it saves you 3 future laps.
In the world of AI agents, spending a few extra tokens on intelligence and planning up front pays massive dividends by keeping the turn count low.
Think of it like hiring a courier to deliver documents. A premium courier is expensive per trip, but they know the city perfectly. They grab the right envelope and deliver it in one trip.
The budget courier is incredibly cheap per trip, but they keep getting lost. They deliver to the wrong address, return to base, pick up a fatter envelope with corrected instructions, and try again.
Eventually, the budget courier makes 3 times as many trips, and every time they return, you have to hand them a fatter, heavier envelope. By the end of the day, they finish later, and you have paid them more total money than the premium courier would have charged.
The takeaway is clear. In agent mode, cost is roughly equal to laps multiplied by a growing, even if partly cached, context. Fewer, smarter laps will almost always beat raw token speed.
So, to recap today, in agent mode, the real cost driver is the turn count, the number of laps, not the price per token.
A smarter, pricier model that finishes in a few clean laps can easily beat a cheap one that flails through dozens, even after prompt caching softens the bill.
But that raises a new question. If every lap resends the whole conversation, and that conversation only ever grows, what happens when it gets too big to send?
That is exactly where we are headed next time. Context compaction, and how an agent stays on the road without losing the plot. See you then.
And that is a wrap for today. If this made AI feel a little clearer, do us a favor and subscribe. It genuinely helps more curious people find the show.
We are learning and building with AI right alongside you, one episode at a time. So hit follow, and we will see you in the next one.